Hello, my name is Shangji Yu. I work in Nanoantennas research group at Stanford University. Today, I will talk about my research on highly confined plasmons in carbon nanotube nanoantennas. In this talk, I will focus on near-field optical imaging of two types of plasmons in carbon nanotubes. The first one is hyperbolic plasmon resonances in carbon nanotube materials, and the other one is highly confined plasmons in individual single-wall carbon nanotube nanoantennas. First, let me briefly introduce near-field optical microscopy. We know far-field image resolutions is compromised by diffraction limit. With near-field optical microscopy or ENSON, we can break the limit and resolve very fine optical features. The idea is to use a very sharp probe to approach the near-field zone and convert the non-radiative field to propagating field. This way, we can detect the near field by measuring the scattered light by a far-field detector. Plaritons, such as plasmon plariton or phonon plaritons, are very interesting near-field phenomena, and those high momentum plaritons can be resolved by ENSON technique. One good example is plaritons in van der Waals material, such as plasmons in graphene or phonon plaritons in hexagonal bond nitride. In this talk, I will focus on ENSON imaging of plasmons in carbon nanotubes. Then we will talk about the sample we will study. We can fabricate globally aligned and densely packed carbon nanotube film. So this is a film, inch scale film we made. This is a photo of that. And if we zoom in and look from top by scanning electron microscope, we can see they are highly aligned. And if we look at the cross section with tunneling electron microscope, we can see they are densely packed. So this globally aligned and densely packed carbon nanotube film are actually hyperbolic material. We will talk about that a little bit later. And we can further pattern them into ribbon arrays by electron beam lithography. And each of the ribbons can support deeply subwavelength hyperbolic plasmon resonances. And ENSON is an ideal imaging approach to study this. So what exactly is hyperbolic material? So in a regular isotropic dielectric material, the three principal components of the dielectric tensors are positive and equal. So this is an equation of the dispersion relation. So it means in momentum space, the isosurfaces are a series of spheres. But in hyperbolic material, the only one or two principal components of the dielectric tensor are positive. It means in momentum space, the isofrequency surfaces are actually a series of hyperbolas. This suggests this material can support a very high wave vector, a high momentum, and very high density of states. Experimentally, we can measure and extract the permittivity tensor by ellipsometry, and we have done this at different doping level, and we show that this kind of aligned carbon nanotube are tunable hyperbolic materials. And the detail of this hyperbolic discussion are published in these two papers. We have done some basic far field measurement So this is a pattern film, and this is a typical image of those pattern film, and L is the width of the ribbon, and this is combinatorial line direction, and we can see with different lengths, we can see different resonance spectra, and we can see the fundamental mode, m equal to 1, or high order mode, m equal to 3 and m equal to 5. So only odd modes show up because they are radiative modes. But the details of this kind of far-field measurement will be discussed later in this session by John Roberts. Please attend his talk. In my talk, I will focus on near-field imaging of these different modes. And first, I will talk about excitation symmetry because this will be helpful in understanding the experimental results. And there are two excitation configurations. The first one is a parallel configuration, in which case the incident wave vector is parallel with a ribbon, and the plasmons are launched by the tip. Basically, you have tip in coupling and tip out coupling, and due to the sample the symmetry, so the near field profile on this sample under this configuration will be symmetric. And there is also a perpendicular configuration. Basically, the incident k vector is perpendicular to the ribbon, so the plasma will be launched by either the tip or the ribbons. So we still have tip in coupling and tip out coupling, like tip launching mode, but we also have directly coupled mode. So this tip launching mode will have a symmetric contribution shown here, but this directly coupled mode will have anti-symmetric contribution. When these two contributions add up, we will see this asymmetric near field profile. And this perpendicular configuration is the configuration we will stay with because this directly coupled ribbon mode is a hyperbolic plasma mode we are looking for. Okay, then we start to map the different modes in the combinatorial film. We started from the fundamental mode in 1.0 micron wide combinatorial ribbon, and we have this far field spectrum, and we can get the raw near field data. It's not symmetric. After subtracting the symmetric component, we can get the anti-symmetric profile, and it match our full wave simulation. And we look into the high order mode, and we did the same thing. We get a high order anti-symmetric mode, and also agree with our simulation. So in this study, we combine the far field spectroscopy, near field microscopy, and full wave imaging, and systematically study the hyperbolic plasma mode and the unsung as a unique tool can help us distinguish the fundamental mode and high order mode. Next, we will move on to plasmons in individual single wall capillary tubes. This type of study started from 2015, and people have explored laminar liquid plasma in metallic single wall capillary tube, reflection phase in capillary tube plasmons, and long linear laminar liquid plasmons in semiconducting single wall capillary tubes. And in these studies, people look for a really good tubes among random tube with random alignment and random length. So one of the important questions is whether there is a better way to systematically study the individual single-wall common nanotube plasmons. Our answer is yes, and we can grow wafer scale aligned common nanotubes. So this is an AFM image of the aligned single-wall common nanotubes, and then we can transfer to a target substrate and make patterns. We can see after transfer and patterning, they are still aligned, and we can control the common nanotube length. Then we can study the enzyme imaging at a high throughput. So here are some data. We study metallic single-wall common nanotubes on hexagonal ball nitride and on Hafnium. We can see this beautiful interference on the individual tubes, and these tubes are only 1 to 2 nanometer in diameter. So the plasmonic wavelength extracted from those data is about 70 to 90 nanometer. But considering the excitation wavelength in free space is 10.6 micrometer, so this corresponds to a wavelength compression factor of about 1/3. This is very, very big. And this large quantity of aligned single-wall common nanotube oxide also enables systematic study and potential wafer scale applications. Okay, in summary, we demonstrate near-field imaging of the hyperbolic resonance on common nanotube materials, and also we demonstrate near-field subwavelength plasmons in patent metallic common nanotube oxide substrate. Finally, I'd like to acknowledge my colleagues at Stanford and our collaborators at IBM, Harvard, and Gwangju Institute of Science and Technology. Finally, I will acknowledge our funding support. Thanks for your attention.